Hello, my name is Jeff Mitchell, and I'm a Cooperative Extension Cropping Systems Specialist in the Department of Plant Sciences at the University of California at Davis. What I'd like to share with you today are some thoughts, principles, and experiences related to cropping systems, soil, crop residue management, and precision irrigation that may have importance over the long term in California agricultural production systems in terms of increasing the water use efficiency. If we look at the various sources of water, storage, retention, these different nodes are going to be increasingly important to users of water throughout our state in the future. One of these systems or storage reservoirs that a lot of times is overlooked, but that I want to talk about with you this afternoon is the soil. And the question I want to ask is, how might we imagine different, efficient soil crop residue management approaches going forward in California as having an important, beneficial, and positive role in helping producers increase water use efficiency. If we think about the many different challenges, all the different factors that farmers have to address and consider and confront on just about a daily basis, I'd like to suggest we focus today our discussion on the soil, implications for soil management changes, for water management, but also on the role that residues, crop residues, and soil biology might have in increasing water use efficiency of production systems. Over the last 2 decades, the term conservation agriculture has begun to be internationally, globally recognized as perhaps having a role in helping producers do more with less. And if you look at this third item here, a definition of conservation agriculture as the integration of ecological management with modern scientific technologies to improve production systems. That's what I want to share with you some experience and some theory about today. The idea of conservation agriculture has 3 main principles. And as a farmer might go from conventional systems or approaches on the left here toward conservation agriculture systems over here, first of all, there's a very deliberate reduction in the intensity of soil that's disturbed. So tillage is going to be less intense in these systems. As a result of that, surface crop residues will tend to accumulate, and they'll be more prominent in the system. Another very important tenet of conservation agriculture is diverse crop rotations. Now, in addition to those main 3 principles of conservation ag, there are other important technologies that are related to the overall goals of conservation ag. The use of integrated pest management, the reliance on very precise, highly efficient irrigation, and also controlled traffic. So in essence, these are the kinds of systems, technologies, and the integration of these practices that I'd like to share some experience with you this afternoon. One of the benefits of conservation ag that farmers, researchers, and many people around the world have seen is the important role that crop residues may have in reducing not only soil water evaporation from the soil surface, but also cooling the soil, allowing for greater microbial biology to exist, for buffering the soil surface from the impact of rainfall and sprinkler irrigation, thereby lessening or reducing runoff, and also increasing some important soil properties that may lead to increased soil water storage. By having surface residues in a production system, they provide a barrier, an armor, if you will, or protection from the drying winds, the heat of the sun. And thereby, one of the things that happens is that in these kinds of systems, the amount of water that evaporates directly from the soil can be reduced. Soil temperatures are lower. There are generally potentially increases in soil carbon, water holding capacity, and also more diverse soil life. Now, most folks who have traveled anywhere through the United States, the central part of the US and other parts, particularly of South America, are familiar with the kinds of systems that farmers back in the Great Plains region have developed over the last 15 to 20 years. It's not an exaggeration at all to say that in the early 1990s, many of the farmers in certain corridors of the Midwest, the Great Plains area, were actually on the verge of going out of business. Because what they had to do is they would grow a crop one summer, then they would have to fallow their fields or their farmland the next summer in order to capture enough rain that would then allow them to farm that third year. And the economics of that fallow system were not working very well for them. So what a number of farmers in that area, by developing high residue, no-till systems with a very deliberate focus on soil care, they were able to intensify and diversify their production systems and are now quite successful. In fact, this quotation that was provided by Randy Anderson, who was a researcher at the USDA Agricultural Research Service in Brookings, South Dakota, really captures the history of what happened in these systems. There was nothing short of a spiral of regeneration of soil and favorable water relations with residues and economic viability in the region that has been very important for farmers there. Now, the research that underlines those improvements in productivity are shown here, at least part of them are shown here. These are data from actually Kansas State, and it compares what happens with bare soil and two different residue types, corn and wheat residue, and you can see that daily evaporation of water from the soil is about half under residues that it is under bare soil. And if you extrapolate those daily reductions in soil water evaporation over an entire season, you can see some savings of water on the order of several inches just by having residue over the surface. Now, in California, the first example where that has actually been shown or seen was a farmer down in Fresno County, in the western part of Fresno County near the small town of Five Points. And way back in 2003, when some of the early work in no-till and high residue systems was being done in California, this farmer actually noted that for his corn crop that he planted no-till directly into high residue, wheat residue, he was able to avoid 2 additional irrigations just by having that residue in the field there that particular year. Another benefit of having residue and increased organic matter in the soil is shown here. Not only can surface residues reduce soil water evaporation, but as you increase the amount or the percentage of soil organic matter, as you get more and more organic matter into the soil, throughout a variety of different textural classes, you're also increasing the actual inches of stored water per given foot of soil here. And this relationship that is shown here in a lot more detail, but it's actually very significant, that by increasing soil organic matter, you're going to have a very pronounced direct effect on increasing the available water that's available to crops. And available water is defined as that amount of water that exists in a field or a given depth of soil at field capacity minus the amount that would be available at permanent wilting capacity. So in essence, available water capacity is the amount that plants can actually take up. Now, I don't want to overstate the importance of this here because it's not easy to increase soil organic matter to these high levels there. But it is a goal that might be important in increasing soil water storage down the road. Now, one thing I would recommend that farmers, and I know most people are already considering this, is to know what your organic matter content of your soil, at least the surface soil, is going forward. These happen to be data from a very sandy soil in Hanford, California, and what they show is some very surprisingly very high organic matter levels already. So a farming system's goal might be over time to try to work on increasing the amount of organic matter that is in that soil. Now, let me show you some examples right now of where these systems have been used. There's no scale limitation to these. Here you have a picture that was obviously staged from Brazil where they're harvesting one crop and planting the next crop into it, right into those residues. The actual data, the adoption trends for these kinds of systems in Brazil, Argentina, Paraguay, Western Australia, and the United States over the last 15 or 20 years are fairly dramatic. These practices, these systems are being adopted by farmers in many regions around the world. And here you see these numbers in the red ovals here are the actual percent of farmland or acreage in these different regions that are currently farmed under these systems. So conservation agriculture approaches are by no means new. They actually, South America currently has about 47% of the total world acreage, with the United States, North America, and Canada coming next there. And it's estimated that over the next decade, the three countries of Brazil, Argentina, and Paraguay are going to have upwards of 85% of their cultivated area under these kinds of systems. So the point is that these systems are out there, people are using them to great advantage. If we look at the history of conservation agriculture and the adoption of high residue, no-till systems around the world over time, you can see that after the Dust Bowl in the 1930s in the middle Great Plains area of the United States, that there was activity throughout those early decades of the 20th century, but the actual acceleration of the adoption of no-till and conservation ag systems really took off about in the 1990s. So while they're certainly not limited around the world, the actual adoption has been a very recent phenomenon. If we look at what's been happening in California over time, that same period, going down here forward from the 1930s, when farmers in California began to rely on pumps for irrigation, there was work early on in the 50s, 60s, and 70s on conservation ag techniques, but it really has been those last 15 or 20 years in California, in the Great Central Valley of California, where lots of innovation with these high residue no-till systems has really accelerated. Now, one thing I'd like to share with you is the opportunity that you have to join with other farmers here in the Great Central Valley, other researchers, USDA, Natural Resource Conservation Service, conservationists, and a whole multitude of upwards of 2,100 different partners who are working on these kinds of systems. And originally back in 1998, we started as a conservation tillage work group, but we recognize that it's the whole system, it's the irrigation, and truly it's the innovation of the entire system that is important there. So I encourage you, if what I'm talking and sharing about with you today is of interest and value, please join our group here. What we've been trying to do over these last 15 or so years is develop research-based experience and information about these conservation agriculture systems. And we started just one crop at a time. How do you grow any given of these crops in the middle line here with reduced tillage? How do you grow them with in high residues? Then how do you take advantage of going through a cropping cycle or sequence to develop and gain economic value from these kinds of systems? The principles we've been trying to incorporate in a systems perspective are very precise irrigation, the use of subsurface drip irrigation, and also or the use of precision mechanized overhead center pivot irrigation. Coupling that with controlled traffic so that there are traffic zones throughout a field that are not trafficking over crop growth zones. Thinking about those four hallmarks of management: soil, water, residues, and soil biology, and trying very deliberately to increase soil life through the use of the tool of no-till. So in essence, those are the kinds of things we've been trying to work on, and we've been working with farmers, as I say, since back in 1998 on a variety of different systems. Originally, it was just planning, thinking about how could you go from one crop to the next crop to other diverse crops in a rotation with less tillage, and how would you configure those crops. The research base that we have is down at the University of California Westside Research and Extension Center in 5 Points, where we've really pushed the envelope of these systems. Here you have on this side of the field tomato residue that's after harvest, and here you have cotton residue. We add cover crops to the systems evaluation in these systems, and we compare them with standard tillage systems. So as you see here, these are truly high residue no-till systems that we've been exploring and we've been trying to develop research information about. Again, year-round soil cover, increasing soil biological activity, having the soil covered by residues to reduce soil water evaporation. It's not easy by any stretch, and some of these techniques are certainly not commercially ready yet, but you can see the kinds of conditions we've been trying to evaluate the potential benefits of these approaches in. Originally, we had a great deal of difficulty in establishing crops with these kinds of no-till techniques, but after a couple of years, we became quickly able to grow decent economic yields with no-till cotton and also tomatoes. One of the things that's happened out of this study is we've compared standard tillage, conventional tillage, traditional tillage without a cover crop, standard tillage with a cover crop, conservation tillage or no-till without a cover crop, and conservation tillage with the winter cover crop. And you can see that very dramatic increases in soil carbon have been achieved after several seasons of doing these kinds of practices. We also have compared the stability of aggregation of soil, and we compared the slake test, which is a very easy in-field kind of an assay, and you can see here that compared to the standard tillage system, the conservation tillage systems and with the cover crops, and particularly the combination of conservation tillage with cover crop, have really increased the soil's resistance to slaking over time. Now, one of the other things we've tested in this work that I think is important in these potentially important cropping systems changes is shown here. This is a challenge that a researcher back in South Dakota gave us, and he says, can we take or do more to take the evaporation component, the E, out of evapotranspiration? And what we've done in this research is shown that by just merely reducing the tillage passes that might go on between, let's say, a winter wheat crop before corn is planted, if you reduce the 4 or 5 passes that might typically be used there, you have the potential to reduce soil water evaporation. Upwards of an inch of water can be retained in the soil there. If you couple no-till or reduced tillage practices by having high residue situations, and you extrapolate the reduction in soil water evaporation over an entire summer growing period, you may have the ability to reduce soil water evaporation on the order of about 4 inches of water. So that's 4 inches of water that would remain in the soil that would not be evaporating, and you'd be reducing the E component there. How does this happen? Well, dramatically lower soil temperatures are seen in a very hot period of September here, just by having that residue over the soil. So reductions in soil temperature and lower soil water evaporation is the way that that's achieved. Now, some suggestions that I'd like to leave you with here in terms of your own planning and thinking about these systems and potential changes and how to learn more about them are shown here. Certainly, there are going to be challenges in terms of transitioning or converting to these kinds of high residue no-till production systems. It's not going to be easy, and therefore planning and devising appropriate kinds of systems that might be most amenable to no-till initially on, that's going to be important. Consider how is it possible in your rotations or your cropping systems to actually preserve residues over time. If you're relying on sprinklers, as we have shown here with overhead mechanized center pivot irrigation, consider applying more water less frequently to reduce the evaporation losses that come from sprinkler irrigation. And also begin thinking about how one might couple no-till practices for selected crops that might be readily amenable to them, to note the use of no-till with precision irrigation to gain better advantage here. Now, none of this is going to be easy, there's no doubt about that, but one of the things that I think successful farmers around the world and those who have adapted and adopted these systems locally in California have realized that it's important to have flexibility and an open mind set in this. And the challenge that Dwayne Beck, the researcher from South Dakota, has left us with is work hard to take the E out of ET and the T out of can't. Now, I am a member and actually the chair of our Conservation Agriculture Systems Innovation Center, our CASI Center, and I encourage you, if you're interested in these kinds of practices, gaining more experience with these systems, to contact us at CASI at either our website or by phoning me directly. Thank you very much.